So I'm gonna wrap up the chapter. We got to see some solenoids. Remember, TJ, what a solenoid does inside of it? How it would pull that rod in there quite strongly and have a solenoid creates a very strong magnetic field in the center, very strong uniform magnetic field in the center. And remember that you can enhance that magnetic field by putting a soft iron core in the center and get a really strong electromagnet out of it. So let's just quick take a look at, let's just imagine a wire coming and making a loop and then going back. So the current is going this way and then this way. And that's not a very good loop, but it'll have to do. Real quick from that right-hand rule that we talked about for creating for understanding the magnetic field around a wire. So if you were to look at the current, it's going this way, so you put your thumb in that direction. And if you look at it here, the thumb is going along with the current, and that means your palm is facing away. And your fingers in both of those cases are coming up through the center of the wire. So think about that. Everywhere in there, you get the field is coming up. Remember, that would be a circle with a dot up through the center of the wire. So, and then outside, it's going away from into the page. So it's going out of the page in the center and into the page. Now, imagine if you didn't take this part right here and just run it back out to the source. What if you looped it around, which I'll just sort of put in a different color. So what if you looped it around and kept it coming around? So and you spiraled it up out of the page. Well, what you'd have is a solenoid, which we got to see in class, and we got to see how it works. And you can see that every loop of wire layered on top of each other would have its magnetic field in the center coming out of the page and a magnetic field on the outside going into the page. So because it's all coming in through the center, you're actually, and because magnetic fields are vector quantities, you can add all those magnetic fields together and get a very strong magnetic field in the center. So if you wanted to talk about the magnetic field around that current carrying wire, then you would just do that mu o I over 2r, and where this is just the magnetic field for one loop. But what if you had multiple loops? So if you had multiple loops like the next screen, where here this is a cutaway, so they cut off half of the solenoid just so you could see what's going on. If you have multiple loops, then what you're going to use in this case is just going to be basically the same exact equation, but what we're going to do, the magnetic field in the center of it would be mu o n I over 2 over excuse me, over L. Sorry. And so that would be the magnetic field in the interior of the solenoid. And there's a little bit of, in your book, you can go over the basic derivations, I think. I'm not sure. But I'll have to look and see. But the big point is this guy right here with, I'll just highlight. We know what everything else is. Mu O is that permittivity in a vacuum, and then I is the current in the wire, and L in this case is going to be that length there. But what's N up there, the highlighted N? N is the number of loops. M is the number of loops. So if you have, one loop and then two loops and then three loops, you basically can see it's a proportional relationship, so it'll become one times, two times, three times as strong. So that's the basic there of what you're looking at. Remember that that these are just this diagram is just showing three very simple magnetic fields due to the wires. But remember, there could be a lot of field lines, and I'm just going to sort of sketch them in here. No, I have them going the wrong way. There we go. And so they would go this way. Let's see if I can get back on the right. There we go. And there'd be a lot of them in that in there is a uniform field. And the other right-hand rule that I taught you, just you could easily read it and get the information, but was just that you grasp the wire, the solenoid, where your fingers will go wrapping around it in the direction that the current is going, and your thumb will point towards north. So very simple little right-hand rule to figure out in the north end of a solenoid. Again, let me remind you that since it's a uniform field in there, and we know that that means that the force acting on a particle, for instance, would be QVB times the sine of theta. And since that force will be a constant, now you can actually apply the concept of such as F equal ma and F equal ma sub c f sub c, and therefore you can talk about mv squared over r. Equations would apply as well. Okay, so that's the basics of a solenoid that I just wanted to get the last part to you. And the other thing was just real quick. Let's talk about what the the magnetic field would look like around some wires. So let's take this as a piece of wire that is going into the page, and here's another piece of wire that is going into the page. Now, with our right-hand rule from the magnetic field around that wire, we would see that that we'd put our thumb going into the page and try to grasp each wire, and we would see that around this one, we'll call this side B and this side A, we see that the field would be going around in a clockwise direction. Remember, it's like a continuous loop. And on this one, so that, take a look right there between, it's going up. That's a key place right there. And on A, we see the same exact thing. It's going in a clockwise direction. So there it is, going in a clockwise loop around. Now look right there. Here you've got, in this part right here, this is going in the opposite direction as here. So we know that we have a north and a south pole basically here. So in other words, they're opposite magnetic poles is what I'm trying to say. And so these wires would push away from each other. But let's look a little bit further out. As you get further away, and you can see a better picture of this in your book on page, I think it's like in the last part of 5-6, you would actually see that these would combine and make sort of one magnetic field loop. And I'm just going to run it around like this. And so, but in the center, close together, they look like that. But as you get further away, it would sort of become one magnetic field. And you could talk about what would happen if they were opposite, and look at a little bit. If they're opposite, then, well, let's just quickly do that. Here, going in this way, and then here, that one's coming out of the page. This one's going to be going this way. And so we'd have down and down. So oh, I think did I say that right earlier back on this screen? I think I said these would attract because they're opposite. I'm pretty sure I said that. And here now we can see these would, the fields are going in the same direction, so they have the same pole. So these would actually push away. There'd be a force pushing them away. And not coincidentally, but what's interesting is that the unit of the amp is actually derived from the force that exists between two long parallel wires that are when the force between them, it's like 10 to the minus, I forgot, fifth or so. Don't quote me on that, okay? But look it up in your book again, but you need to know that it's a good box. I know it's in a gray box, one of those gray boxes, and it's a little esoteric number, but I'm not sure you need to know about the number. But here's the deal: that I think there's a meter apart, 1 meter apart, and when these wires have a force on them of some magnitude, then they call that an ampere. So that's the origin of the ampere. When that force gets to a certain amount, then they call that the ampere when they're 1 meter apart, and it's equal to 1 ampere. So okay, so that's basically really it. You might want to look at a couple things. I don't need to derive this for you. I know that, but if you think about this, you would have a magnetic field here of B equals mu O I over 2 pi R, and the same for here and here. You could apply it in both places. And then from that, if you recall the force on a wire, a current carrying wire in the presence of a magnetic field. So let's think about it. This wire is carrying a current, and it's in the presence of this field. So that is B, I, L, sine theta. And so then you could substitute the B up here into here, and you could derive an equation to find the force on one wire on the other. And we can look at that. That's not something we try to do here. That's better, a little bit more teacher directed probably. Okay, so that's all of the chapter. Again, let's just sort of look at what you need to know real quick. I'll just go back through one loop wire. Look at where the field is, and then when you get a bunch of loops, you can add them together, and that N stands for the number of loops. There, we'll get an S on that, and that's a uniform field in the center, and then magnetic field around two current carrying wires, and see that they're going to push. These will attract together, so the force here and the force here, and that's pretty much it. And just make sure we'll go over some more on the right-hand rule so you can get some right-hand rule practice. Don't be afraid to look online. You know, I'm not the only source. There's lots of great little tips and practice on right-hand rules on the internet. Okay? All right, that's it. Good night.